Okay, guys, that's 11. We'll start. I guess other people can rock it anyway. This was somewhere between 60 and 90 minutes, but I guess, you know, who'd prefer the 60 and who'd prefer the 90? Because I can talk in great detail or I can sprint through it all. So, you know, who'd prefer the 90 and who'd prefer the 60? Hands up if you just want 60 and you've got to get out of here. Cool. Okay, so you'll get the Blitzkrieg version anyway. So that's about 100 slides in like 60 minutes. So let's rock and roll. Okay, deep drilling. I'm a drilling engineer from Warraki, geothermal drilling for 30 years. That's our rig, currently working right outside the Warraki Power Station. Beautiful bit of engineering and some steam pipes. So hopefully by 60 minutes you'll have a bit of understanding what the hell that thing's doing. That's me. I'm a graduate from 1994, so I've sat in the same seats that you guys have had. I've been doing this for 30 years. As soon as I graduated in 94, I just basically got straight into it. A lot of people who taught me are dead now, so I'm kind of this rare thing who's got a long experience, bloody more than everyone else. So there's a saying in the Valley of the Blind, the one-eyed man is king. That's kind of me. So I've been doing it a long time. So I live in Taupo, and I've got a wife and 4 good boys up there. You guys are engineers. And I've got mad respects for you guys and what you're doing. I mean, it's a hard degree. We know this. It's probably the hardest degree you can do. And, you know, you're not handed to it in your plate. You actually got to work your asses for it. And when you leave here, you're going to be really instrumental in society. So, you know, when you get out of here, you need to be the movers and shakers. You're going to be the movers and shakers. For the New Zealand economy, for everything. Normally I run this as a blurb about climate change, and like you guys, I want you guys to be the motive forces for climate change as well. You're going to go into a variety of other things, but, you know, doing what I do, you know, focus on fixing the planet and, you know, decarbonising, it's important. So, you know, if you ever get a chance, just focus on something like that, some part of your careers. Okay, so geothermal. Geothermal is anywhere. It's anywhere in the world. I mean, underneath your feet is this molten magma, and you know, you drill down deep enough, you're going to hit it. But what we're doing is, it comes to the surface in places. So we've got this ring of fire floating around here, which is plate boundaries, and it's just associated with all this volcanism. So that's where the heat is close to the surface. So that's what we're doing. We're utilising the power from that to actually use it for power, for energy. So they're all related to plate boundaries. And it's interesting because you need those oceans to allow the plate boundaries to subduct. So you'll never see a plate boundary happening on dry ground. It needs the water to actually lubricate it as it goes in. And what that does is the water actually makes the rock melt at a lower temperature. And you end up with these bubbles, like, well, you've seen lava lamps. It's exactly what it is. These big blobs of magma flowing up through the crust. Now, if they come to surface, they're a volcano. But if they stall, they can't get there, then they just sit idle, and that's when they create a geothermal system, because they sit there underneath the ground and they heat up the groundwater. So this is the Taupo volcanic zone. There's a range from active volcanoes at either end and a whole bunch of sort of geothermal systems in between. So geothermal reservoir, the classical geothermal reservoir that we need needs 3 things. You need the heat, so you need the magma there, and you need some fracturing. You need the rock broken up so it has flow paths, and you need the water in there. There are a lot of companies that are trying to look for gold out there, trying to just use the heat and make their own fractures and put water in there. And that might be the future, but it's a very expensive way to generate. It's kind of this sort of it's like fusion. It's like coming soon to a town near you. But so what we're doing here is we're just using this classical. We've got the heat, the permeability, fractures, we've got water in there, and so we can turn that. And that creates this geothermal reservoir. So a geothermal reservoir would look like that if you just carved away the rock. This is an interesting one, because there's one side is Warraki and one side's Tauhara, and they join up at the top. So this is full of nice, good steam. We can go and utilise it, and we can make electricity from it. So we've got the steam underground. This is pretty straightforward, through a turbine, generating electricity, and then what they used to do is just put the water in the river, but the water's full of chlorides, full of borons, arsenics. So what we do now is we re-inject that water. So those sort of elements just get pushed back down, and it keeps pressure control as well. But you see the key part of that are these two wells. So you've got to actually get to the resource and use it, and I guess that's what we're going to be talking about today. Comparison of geothermal to the other renewables that everyone talks about. You know, here on the radio they talk about wind, solar, hydro. Now they're all good. I'm never going to bag a renewable over a non-renewable energy source. But, you know, solar, if it's night, doesn't work. You know, wind, if there's no wind, doesn't work. And hydro, if there's not rainfall. We have major issues in New Zealand with climate change where the hydro lakes are down and you can't generate as much electricity. So each one of those has kind of a little compromise. The only one that's actually going to be like really reliable base source, climate independent, is going to be geothermal. And many of those are required, you've got to build in a certain location, we're no different. But in terms of actually being a renewable energy source that you can actually bank on, it's fucking good, man. So yeah, I'm really happy to be part of it. Quick history of geothermal in New Zealand. Sorry, this is the whistle stop, 60 minutes. I'm going to go balls out to make sure we can get done in an hour, okay? It starts in an interesting place in the 1940s, and it starts with this fella. Yeah, that's the reaction you usually get. Now, why is he important to geothermal in New Zealand? Because in World War II, we had electricity shortages, manpower shortages. We couldn't ship shit anywhere. And in New Zealand, there was brownouts and blackouts, and there wasn't enough electricity. And so, you know, we were fighting the war, and in New Zealand here, we were not in a very good state, power-wise. Now, an interesting part of it is the New Zealand Expeditionary Force went through Italy, and they fought the way, and they kicked the Germans out of that, and they went up and they found this place called Larderello in Tuscany. And they'd been drilling geothermal and had geothermal power production there in about 1922, I think. So the engineers, you know, the army engineers went through and said, holy shit, this is really cool. So we came back to New Zealand, looked at our map of where we could drill, and they decided on Warraki. And it was a very fortunate kind of decision at the time. So May 1950, drilled the first bore 1. It's only 200 metres deep, bugger all. And yeah, excuse the units, 4-inch casing. And we found something. And that photo should be in the National Archives. I mean, look at this, guys. This is called the over-the-shoulder method of well control, where you run away while the well blows out. That's such a cool photo. And so, yeah, we found steam at Warraki. And we've kept that well. It's abandoned. We've kept it as a homage to those pioneers from 1950. And that's just sitting there in the Warraki steam field as a little shrine to be cared for, New Zealand's heritage. And from 1950 to 1953, that's what the valley looked like. In 1960, it was just full of wells. It's just insane. You know, we just went from strength to strength. In 1959, I think, is when they started producing. Second geothermal power station in the world. It was the first one to have two-phase fluids. I guess you guys probably know turbines. You can't have water droplets going through turbines. So Larderello, the steam was dry. Take it out of the well, put it through the turbine, no problem. But this one was wetter. It had more water droplets, so we had to invent a separating system to actually get rid of the water and take the dry steam to the turbine. So that was the first for what we've done. Station's still running, but it's due to be shut down in about 2 years, which to me is really sad. And that's what the whole area looks like now. So that's the Warraki Valley you can see here. And they're a location of the wells. So it's a real pincushion. You know, we've got really, really good data. The funny thing is that we've got all this data and our reservoir engineers are finally, after all this time, starting to get an idea of what's happening downhole, underground with all the water flow. So it's taken, sort of 60 years or so for these guys collecting all that data to even start understanding where things are happening. Example of that is Warraki 1 was here, and we're drilling out here now, and we're finding the hottest parts of the field are actually way out here, and we think that the water flow is coming in from here. So yeah, there's a lot to be known and learnt, but you don't have the ability to actually peel away the layers. You've just got to go drilling. So now geothermal-wise, for contact, we've got Warraki Power Station, the old girl, Te Mihi, which is another extension of Warraki, Ohaki, which is Oh, I won't talk, that's a problem child, we don't want to talk about that, we don't talk about Ohaki. Te Huka, which is a new one on Te Ahara and Poipi. And what's not shown up there is the last 10 years of my life we've been building a new power station at Te Ahara, and yesterday they finally put steam into the turbine. So in the next few weeks, months, we expect that to be turned into another 150, 155 megawatt geothermal power station. So how do we drill these wells? Right, so you've all done a twist drill, got the Ryobi at home, drill a hole in the ground. So you need three things. The way we do it is we call it rotary drilling. There's a variety of different types of drilling, but what we're doing is rotary drilling. So you need the bit, and you've got to put some weight on the bit, and you've got to rotate it. And the last part is that's going to dig into the rock. You need a way of cleaning out the cuttings. You're going to need to clean the hole. So for a twist drill, that's easy. The helix just pulls all that stuff off, the swarf off. But if you ever need to drill further than your twist drill, then we need something a bit more clever. So this is the drilling system. So this is how it's done. So we've got the drill bit at the bottom of the hole. Now we've got these things called drill collars. Now they're basically really heavy pieces of pipe screwed together. This is all hollow, and they're designed for weight. And they will push the bit onto the bottom of the hole. So you cannot push the stuff from surface because you can't. Oh, sorry guys. Does it matter? You can hear me with that anyway, can't you? All right. Sorry. Right. Better? Thank you. So drill bit on the bottom, which is breaking up the rock. Now the drill collars are there for weight. So what you do is you sit off the bottom of the hole, you zero your weight indicator, and then when you slack off 1,000 pound of weight, sorry, again, American units, then you know you've got 1,000 pounds weight on bit. So what you're doing is you're adjusting, slacking off that weight to actually push the bit onto the bottom of the hole. You do not push from surface. The drill pipe has to stay in tension. The reason for that is buckling. Because you're rotating it, if you had that in compression and it buckled, it would fatigue off. So the whole lot is you're just using the drill collars just to pull the drill pipe in tension and rotating it. You can actually put drill collars in buckling, but it's pretty hard because they're really heavy and stiff. That goes up back through the surface and you see this is actually a hollow pipe, and the drill bit has some holes. And so you end up with a circulating fluid. So you've got this tank full of, we'll call it drilling fluid for the time being, normally mud, but it can be other things, picked up in a mud pump, and then that's pumped down into the drill string, and it picks up the cuttings and it washes them. So it washes them up the annulus as you're drilling to clean the hole, and they get to the surface and they run down a line, and they get to a solid control equipment which gets rid of the cuttings, gets rid of the sand, gets rid of the fines, and kind of cleans the mud, and you just recycle it. The only thing that's missing there for geothermal is a cooling tower. We have a cooling tower just to knock the heat out of it. So the whole point is it's just hollow pipe, and you just be able to pump through that, so you can add another jointed pipe. So drill bits come in three main flavours: the tricones, which have little teeth. They're on bearings, so as they push them on bottom and they roll, they'll crush the rock. PDC is a drag bit. So it doesn't have bearings, doesn't have seals, so it's a lot more temperature tolerant, but it's easy to break. It's kind of pretty fragile. And you get this thing called a core head as well, which drills a nice fat core. So that leaves the centre of rock in the middle. So that's tiny little industrial diamonds, and so they'll grind away. But yes, the things they've got in common are they've got the holes for the fluid flow in each one. They've got a cutting structure to drill the hole. You need to have gauge. They go in that size, they come out that size, because no one wants to drill a tapered hole. And yeah, that's it. So these are drill collars, just for the threads at the end. So they're basically really mostly steel with a little bit of hole in the middle. But we need those for stiffness, about typically 9 minutes length, and we need them stiffness and weight. And so that's all they're doing. And we can use those, I'll talk about later, about what else we can use that for to help with the drilling trajectory stuff. In the bottom part of that, we have something called a bottom hole assembly. We put in some other tools, and that way we can actually control and manage what we're trying to achieve. But yeah, drill collars sit at the bottom, maybe 100 metres. You typically have 100 metres of these drill collars, and then you go back up to the drill pipe, which is kind of has a pretty hard surface. It's got to have torsion, tension, pressure, fatigue. It's sort of susceptible to friction, wear. And the guys on the rig are called roughnecks, and the good reason they're called roughnecks is because they are rough as guts. The only people I've ever seen that can actually bend a drill collar are roughnecks. So these things have got to be tough enough to actually withstand the idiots that actually use it on the rig. Sorry, don't tell them I call them idiots. They're great guys. Yeah, so the drill pipe, and that connects. Basically, all that's doing is connecting the drill collars downhole with the rig, transferring torque, transferring tension, transferring fluids. And you might have noticed that the tool joints are all tapered, and that's actually pretty clever. It means that when you're on the rig, because you have this one sitting in the rig floor, and then you've got to be able to stab that one in to make it up, so it makes it easier for this guy to line it up, stab it, screw it together, so they're good for stabbing. Reduces the number of turns to make it up. And it puts, for fatigue and strength, it puts the strongest part where it's needed. So the weak part there is that part of what we call the pin, so it makes that fatter, and the weak part of what we call the box is that part there, so that makes that fatter. So it makes a strong connection. So everything we run is these tapered threads, which is kind of cool. So how to drill it down, apply weight on bit, which is basically slacking off some of the drill collar weight. So you drill your single down, clean the hole, and then what you do is you pick up, pull back a certain distance. And we've got these things called pipe slips, which is have a grip surface on the inside with a tapered bowl, and that means you can support the drill pipe off bottom. And so you unscrew the top drive, put another jointed pipe, put the top drive back in, and then drill down another single. So you drill it down, clean it, just pull it back, hold it off bottom, put another one in, and so you end up just adding them like this. But drilling the hole is not what we need. Drilling the hole is not building a well. We need to build the well structure. So we drill that down to whatever depth we need. And we pull everything out, leave the open hole, and then we run a thing called casing. Casing is just smaller than the hole size we've drilled, but it's steel and it's like 12 metre lengths and all threaded and screwed together. And so we're going to run that into the hole, and then we can cement it in place. So cement around the outside, nothing on the inside, let it set, and then you've got yourself a pipeline. You've actually cemented in a pipeline from surface to wherever you wanted to go. And now you've built a well structure. So casing typically looks like that, 12 metre lengths, whole range of sizes, weights, grades, and threaded every 12 metres or something like that. And those connections are quite important to the strength of a geothermal well. I'll cover that in the end. And how we cement it. So we need lots of cement, and because particularly for geothermal, it's hot, we can't just have it sort of mixed up like 5 hours and then send it down. You've got to make it quickly, and because you've got a fixed amount of time before it will set. So we end up with a system called, we have cementing units. And what that does is just take bulk cement and all pre-mixed water with a whole bunch of chemicals, mix it together and then pumps it away. So it's fresh cement when it goes in. So you pump that down the inside of the casing, and it tends to come up around the outside. And then what we'll do is we'll put in a big rubber plug. Put that in and then push it down with water. And so that means the cement's all the way around the outside, and you've got water on the inside down to the plug, and so you don't have to drill out the cement on the inside. And cement sets, you're good to go. Key part is all that stuff on the inside is drillable. It's rubber plugs. We've got these things called floats here, which are non-return valves, because we're dealing with like 1,500 metres of length of pipe. If you put cement on the outside, raw on the inside, the differential pressure is huge. They want a U-tube, so you need to put non-return valves on there to actually stop them from backflowing. And to be perfectly honest, for the bigger casing sizes, this stuff floats. I learned that the hard way when I was pumping, and all of a sudden the casing started to come out, and I stopped, put the pump on, And I hadn't even thought about that. It floats like a ship. If you've got so much density around the outside and not enough weight on the inside, yeah, so that was... sometimes you learn the best lessons by making mistakes, let's say that. And then finally, what we'll do is, for geothermal wells, we put in a liner. So this is just really dumb one. It's just a bunch of pipe with little holes drilled into it that sits on the bottom of the well. The holes just mean that whatever you pump in goes out into formation. Everything in formation can come into the wellbore and it stops the holes collapsing. And so that's how you'd finish it. And then you put a master valve on the top, like a wellhead. Really simple. One master valve down through the middle so you can run tools in and out. Two side valves so you can put water in, you can take gas off, you can measure pressures. This is a whole much more production equipment, but the wellhead that I complete is just in here. Yeah, so you've done that, you've got the liner in, you've got your wellhead on, you've got a completed well. Easy. And when we're actually going off and doing this as a work, then we're forecast how many days versus depths, because wells are expensive. So I won't explain now, but you'll see later, you don't just set one casing, you've got to set multiple casings. So your days versus depth plot would look like drill a section, case it, cement it, put on your wellhead on, drill the next section and repeat, and you sort of run down. So when we're actually doing this, trying to be very aggressive on days versus depth is important because it brings the cost down. And we get competitive with other drillers and other drilling engineers about being able to drill deeper, faster, better. The well quality is still the most important thing, but we've got that baked in. So yeah, we end up with this days versus depth chart that we try and maximise. And what do we use? Drilling rig. Not great. So they're really four machines that sit out in the middle of the rain in the paddock. It's a hoisting machine, it's a rotating machine, it's a pumping machine, and a well control machine all sitting in there. So hoisting, old school, used to look like this, with like a crane with a drum and a travelling block. Modern ones look more like this, hydraulics, direct application to a hydraulic ram. The things that I care about in this as a drilling engineer are going to be hook load, how much can I pull? What sort of tripping speed can I do? Because if it's 10 tonnes but it's going like this, then because you've got to run in and out quite quickly, you want to go and do a tool change or something like that. Combine those two together and you've got horsepower, so the horsepower of that system must be enough to actually be productive. And for this type of rig you can apply pull down too, which means normally if you're drilling one of those at your start and you've got like one drill collar and it's very low weight and you're not getting anywhere with this one, you can actually just shove it into the ground, get your rate of penetration, ROP up, and you can start drilling quickly from the start. Plus other things too, like if you end up with a well control situation that wants to push everything out, then you can hold it in. So the old way of rotating the drill string was something like this. It was a squared piece of pipe screwed onto every single jointed drill pipe and then put into this Kelly chuck. You rotate that, it rotates the drill string, and you drill that one down and then pull it out. And then you've got to put a piece of drill pipe between the Kelly and the rest of the drill string. Pretty old school, but it was invented, like I said, by old grandpa back in about 1903 in places like Spindletop. Pretty effective, but we've done better than that too now. We've got this thing, top drive unit, which is basically the trouble with the Kelly is you can only do it over a short distance. The top drive, you can rotate the pipe the whole way up and down through the mast, which means if you're fighting a well and you want to back drill, you could only back drill a little bit until you hit your Kelly point and then your Kelly chuck was coming out. You couldn't rotate anymore. There's a top drive, you've got what we call trebles, 27 metres, and you'll just back drill the whole lot out if you're having drilling problems. So no one uses Kellys anymore, top drive is it, it's really cool. Another way of turning the bit is a downhole mud motor. So it's basically a moino motor where you pump mud through it. It's got a bearing system and the mud goes through stators and rotors and that'll turn the bit independent of the drill string. And there's a little exclamation mark there about, you can put a bent housing on there too, so you can put a little bend in it. which is kind of useful coming up. For the mud tank, sorry, for the mud pumps, a key thing we need to think about is annular velocity. You're trying to lift all this cuttings and stuff out of there, and they want to fall through it. So you need to make sure your annular velocity is greater than the rate all these cuttings are falling through your drilling fluids. So you need to have a minimum sort of pump rate to actually achieve that, or you can manage your slip velocity, how fast those cuttings fall through that fluid. And particularly important when you're drilling a big bit. This is a 36-inch bit, so we start a lot of our wells with that one. But you can imagine the area of that, and you want to have a high annular velocity, and your flow rate's got to be really, really high, right? So mud pumps are a really important part of our system, particularly for geothermal. Most rigs used to have 2, now we have 3. And they've got to pump a lot of higher flow rate, but also through that drill pipe. And the drill pipe's, you know, you're talking about 2 or 3 kilometres of like pipe that's only like, I keep thinking inches, sorry, 3 inches diameter. And so your pump pressure is high as well. So you've got high flow rate and high pressure equals high horsepower. So these things are like 1,000 horsepower each. They're just probably the biggest sets of bloody horsepower actually on the well side, but they're really important. They're like the heart for the drilling rig. So yeah, we need to have that. And so what are we pumping with that? Oh, sorry, drilling fluid. So normally you pump drilling mud. And what that does is that gives you a whole lot of benefits. It's stuff, you mix a whole bunch of powder in with the water, and it makes consistency like house paint. And what that does is really, really reduce that slip velocity. So that's why for those big hole sizes, the slip velocity is low, as you don't need much of the annular velocity to lift it out. So it helps you cleaning. I should have put these in the other order. But a big problem with what we have is lost circulation. I said before, you know, we're looking for, a geothermal system has fractures, and that's what we're looking for. And down in the open hole section, that's good, because that's how we want to produce the well. You know, fluid into the well, fluid out of the well. But that, unfortunately for geothermal, happens everywhere. Anywhere, like from surface down. So quite often you end up with these problems with lost circulation, and it can be really, really hard to cure. You know, what we'd normally do is you might put a cement plug in there, you might put stuff called lost circulation material, which is like, the best one we've found is sawdust. But we've been desperate. We put rags and undies and t-shirts and rocks. I mean, we had one there, and I put 40 cubic metres of rock down one well, and the hole size was supposed to be like this. You imagine 40 cubic metres, right? That's like a shipping container, and it brought the bottom, the level up by that much. So these fractures are massive. So yeah, we're dealing with this, and it's a real problem, particularly in geothermal. But how do you drill in that condition? So we have to drill with water. So that's the way we fix it is drill with water, because we can't afford to keep putting these chemicals in down there. So water is free and plentiful, and so we'll do that. The problem with that is it makes the slip velocity high, which means your annular velocities have to be really high. Or you'll drill it with that and put a little bit of a mud sweep around. And aerated, which I'll talk about later. Aerated is a way of dealing with if you lose circulation. The last machine is well control. This is my mate Sam. This is a blowout preventer. Normally that would have a rig sitting up on top of it, but in this instance we had taken the rig away and kept it in place. And so it's kind of, the big round part at the top is called an annular, which the blue piece is actually rubber. And so what happens is you put a hydraulic fluid into the bottom of this, and that yellow steel cylinder comes up and it crushes in the rubber and closes around anything in the well. And that's good because it can close around square pipe, casing, drill collars, even nothing. If you really wanted to, you can actually completely close off the well with that. So that's your annular preventer. So upside is it's flexible, it can close around anything. Downside is that it takes a lot of fluid and it's a low closing time. And if you lose hydraulic fluid, it's going to open. So you match this with a ram BOP, which has, the bottom part is basically 2 slabs of steel on hydraulic rams. You just slam shut, bang. And so that's a really quick and easy way to close in the well. But if you've got drill pipe in there, you can't do that. So they have the top one as a pipe ram. It's exactly the same, but it has a cutout for the drill pipe size. So that runs in, closes around the drill pipe, and very quick to shut. Thing is, it's instant and very low pressure, low volume, and if you lose pressure, it'll stay shut. So we always have these two, like a married couple. So you always have the ram BOP on the bottom, annular on the top. And that's run by this thing called an accumulator, which is all the energy you ever need to close those in, stored off to one side. Because I think they found out the hard way, if the rig explodes or has a fire or something happens, you can't afford to have a pump or a generator running it. So you push a button and all of a sudden that hydraulic fluid just shuts those. So it's something that they learnt from, I guess, the hard way back in the day when they first did oil exploration. But so yeah, this is our well control system. Now I talked about how you could use, why it was special that you could have a mud motor with a bend. And the reason is with this, because you put a mud motor with a bend, coupled with some downhole electronics, and those downhole electronics will tell you the tool face, your inclination, your compass heading, and temperature, and a few other things as well. And so that can talk back up the surface, and then all of a sudden you can steer where that well goes. So all of a sudden you want to build, you just set up, I want to go north, so you put the little bend going north, and you'll just track it, and you can see where it's going. Now say, I want to go east. And so you can actually make these really complex three-dimensional shapes down hole now with measurements while drilling and this bent motor system. So we call it a steerable assembly. And at the moment, I would say 90% of our wells are built like that. So yeah, we're doing a whole bunch of interesting kind of complex shapes, things like that. So the wells just don't go down; they go left, right. Stories about them going out and turning like 90 degrees. Yeah, but good part of that too is it tells us the temperature. And why do we want to do that? Well, if I've got like a fixed platform or a fixed pad, I can set and I can drill and intersect a whole bunch of different areas in my field from one pad. And imagine, we're not a platform, but we've still got limited site access. So all your pipes come to one central well site, but you've actually gone and drilled a whole bunch of other places. A lot of the fractures that we're looking for are actually faulting. So this is a well that we're going to drill in a month or two. So the idea being that we actually can cross all those potential faults, and the fault's where the permeability is, so we'll go across it and maximise our production. In oil and gas, they have this thing called geosteering. So they've found an oil sand, and they actually have feedback electronics, and this thing will actually, like a guided missile, it'll find its way through the middle of that oil sand. So when they're finished, they might have 500, 750 metres of oil sand content. So yeah, no, it's really powerful, and that's our most extended reach well, 2 kilometres in Warraki. But in oil and gas, they're going out like 9, 10 kilometres horizontal. You think, how the fuck can you do that? And the idea is it's not weight, it's drag. I said, if I put an engine block on the ground, I couldn't lift it, but if I put some oil on it or some roller skates, I could probably drag it, pull it along the ground. So it's the same theory anyway. But yeah, they're drilling some really insane sort of well profiles now. And as an engineer, what do you care about? You want to make sure you don't exceed your pickup weight. Some of them are so extreme that you won't be able to get stuff in. Your slack off weight will go to 0. So you're trying to run in and it won't run. Running at a torque is a big one for us. So this is a torque and drag program. So we'll put in a profile that we need to drill, and we'll work and do the numbers to make sure that we can actually get this thing drilled and completed. Also in the BHA, I think I'm on time for finishing. You can put stabilisers which hold the drill collars off the side of the hole and kind of keep in a straight line, and I'll show you why that's cool later. Have these jars and accelerators. Now they're like insurance policies. A jar's like a piece of locked collar that will release after a certain amount of load. So if you get stuck, what you do is you pull on it and you put all the stretch in the drill pipe like a spring, and then after a certain level the jar will release, and it comes up and it's like hitting a big fucking sledgehammer. And it gives us a big whack and it shakes the ground, and actually it's like an impact tool to get you free. And you can put other boring things like hole openers. So this is all in the BHA, maybe in the bottom 50 metres. You put all these things in there, motors, jars, stabilisers, a whole range of stuff. And that's kind of what drilling engineers like bread and butter is doing. So we'll put this in the bottom of the hole to actually. And stabilisers are interesting because before they actually had the mud motors, that you'd have to use the stabilisers for sort of trajectory control. So if you put the stabilisers like that, there's nothing to bend, and it'll just go in a straight line. But if you take the middle one out, the middle sags, and it sinks, and that pushes the drill bit to the high side, and that will start to build. And if you drop the bottom one out, then all that extra drill collar weight's sitting on the bottom of the drill bit, and it'll drop. So you can actually control whether you're building angle, dropping angle, holding angle, just by sort of placing these stabilisers in the well. So that's just drilling. Before I go to anything else, is there any questions on that? Because the next part's just going to be why is geothermal different?
How do you line the wells when you've got like that 3D shape? It's not just a straight.
How do you what, sorry?
Like line the wells with concrete.
Oh, yeah, no. It's the second part of it is I'll do the torque and drag to prove that I can drill it. Second one is to make sure the casing go in there. And the casing's stiff, but if you went and put like 200 metres of casing on the ground, you could probably push it. So yeah, they go around, and then the engineering part of it is to look at the bending stresses. You know, as you bend it, you're going to put compression on the inside, tension on the outside. So generally they will follow the track unless you're doing something really silly. If it's really a sharp angle, it won't go. But yeah, part of the engineering is to make sure that we can get the casing in once we've done it.
So what part of the blowout projects are found in the deepwater horizon?
The shear rams, really. There was a lot of things that went wrong. There were 7 barriers that failed. But the last one, their Hail Mary Get Out Jail Free card, was the shear rams, which are a giant pair of scissors, and they're designed just to actually snip and cut all the steel and give you a seal. And that was their absolute fallback. But what happened was, because they had internal pressure inside the drill pipe, it had buckled and it had pushed to one side. And if you imagine a pair of scissors, it was basically the pipe had jammed up in the very centre fulcrum of the scissors so that it couldn't actually cut it. So yeah, that was the final last part. I mean, there are a lot of other barriers that happened there as well, but yeah, that was the main one.
For geothermal well development, do you need to pump any proppant in to keep any of those sort of fishes and stuff open?
Not really, no. They're mostly already there. You know, we're blessed with lots of permeability. Yeah, so we haven't to worry about it. And yeah, that's a whole other story, but no. Yep, so what are we looking in there? I mean, geothermal I'm comparing this to oil and gas. It's a lot more complex. It's lots of lavas, hard rock, you know, sort of major earth-shaking events, and they're all mixed up. And, you know, we can have different geology. I'll skid a rig and a whole formation is missing. So it's really kind of complex. The formations are quite hard, which makes the drilling slower, and a lot of variability. And of course, the permeability, which is just the bane of what we do. Like I said, it's just, you know, we lose circulation all the time. So I guess this is a typical temperature profile we'd expect to see in a well, so colder surface, but pretty soon builds up to a reasonable temperature with normally conductive heating. And I mean, what's this one? This is up to 250. I mean, our temperature ranges from 180, about 310. Yeah, so it sits like that, and that would be a static well condition. You can see here, this is the pressure curve, and it's built probably a column of gas and steam. So that's got a wellhead pressure of 40 bars, but it's cold, so it's not steam, there's gas. We get gas in there as well. And of course, what happens when we decide we're going to open the valve and let that rock, then we get a discharging profile that looks significantly different. You look at that temperature change at surface from there to there, and you know, this stuff coming out, and you know, the ground is there ready to come and, you know, show you who's boss. But yeah, so we get this massive temperature swings when you're going from quiet and quiescent to actually fully discharged. So we need to manage those temperature changes, or else we can break our wells.
Sorry, just on that pressure, so for every 10 metres, if it was just static water, you'd expect 1 bar per 10 metres?
When it's cold, but when that water gets hot, you can get down to about 0.7 SG.
Are these pressures in addition to what I'm saying, or are they the actual?
That's absolute pressure. So,
Absolute pressure,
so I mean, if I was down here at 1,050 metres, we're looking at 70 bars. But that's balanced on a reservoir. There'll be a reservoir pressure. There's probably a fracture at that point, and that's showing a reservoir pressure. And the difference in those is the hot and cold condition of the fluids.
So 70 bar is actually lower than the 100 bar you'd get if it was static cold water, yeah?
Well, yeah, we're not dealing with water level at surface. Okay, so most of the formation pressures down there are subnormal, so they're like, in that case, that's getting a water level of 250 metres. So that means that it's like the ocean, the swimming pool tank is down at 250 metres. So it's depressurised, but then, when it's cold, that is going to be 1 bar per 10 metres. And down here, it's going to be like 0.8 bars per 10 metres. So the density changes. The pressure's...
Down to 250 metres then.
There's no pressure, and then it's building gas and steam. Yeah, but the pressure is controlled by down on connection with the reservoir, and that drives everything else in the well. Yeah, not only that, we've got CO2, which I think I showed you there. There's gas, which has column of gas, but it's cold, so it's not steam. We have H2S. Now, the H2S is a concern for us because it's the one thing that could kill every guy on the site. And once in a blue moon overseas, it does. They have an H2S release in a well, and then everyone dies. So we've got gas alarms, and we've got procedures, and we've got a lot of procedures to make sure that we keep people away from it. It has an effect on the steel on the casing, the steel on the wellhead, the drill pipe we use, and even the cement we have to use. So the gases are kind of a major pain that we have to sort of engineer around. Other interesting thing is the wells have the ability to have pressure quite shallow as well. Oil and gas, you might drill down and say, I've got a cap rock, I've got nothing, I'll just drill to 1,500 metres, set one casing, and then drill through that, and I've got pressure. As geothermal is different. We can get sort of like appreciable pressure anywhere from surface in a lot of places. So, those temperature and pressure plots are really important for us when we're designing wells to get in, make sure it's done safely. One of the first things I used to think when I hadn't done this before is, how the hell do you drill it when there's steam down there? And the cold water is a trick. You've got a jug boiling, which is your reservoir. So how do you take it off pressure? You pour cold water into it, stops boiling. So our well control technique is to continue putting cold water down there. You drill it, and when we're drilling it, we're just keeping it cold with cold water. And then when you turn the water off, anywhere between 20 seconds and like 2 weeks, the well will come on pressure normally. But yeah, so well control for us is cold water. And to do that, we need to have a high capacity system. So for any of our fields, we build this. High-end water reservoir feeding to the well site. So the pump can go to the well site, the reservoir can go to the well site. And we need to have that, not just for well control, but we've got to drill blind. When I said we've got to drill these wells, but we don't have enough, we're not getting returns, so every litre of water we put down there to clean the bit is gone forever. So a really unsung hero of our geothermal drilling is having like these high capacity water supply systems. And we're looking at 3,500 litres a minute consistently. So yeah, we put a big investment in that. And what happens when you lose well control? This is the Warraki Rogue bore, which amongst geothermal people is famous, and I bet none of you guys have ever heard of it. It's outside of Taupo. It was about 1961, and they were drilling away. And if you're interested, there's a video on YouTube with this one from the Ministry of Works, the government. It's 15 minutes long. It's pretty cool. So they're drilling with the rig, and they took pressure, and they couldn't control it. And all of a sudden, a fumarole broke out on the side of the well side. And they're like, oh, that's not good. And the fumarole got bigger and bigger and bigger. So that's the cellar where the rig was. And this wellhead is shut in, but you've lost control because it's not coming through the casing anymore, it's coming through the dirt. I don't have any control on the dirt. And so we went from that to that to that. And if you want a sense of scale, you see the little dudes there? It's absolutely bloody terrifying. And I remember seeing this when I was your age, plus about 2 or 3 years, and I said, it's never going to happen to me. I cannot let that happen, because that gives you the shits. And luckily, all the photos of these major disasters in New Zealand's history are black and white, which I'm hoping means that I'm not doing a bad job at my job, but yeah, I've still got to get to the end of my career. And yeah, at the end of it, that's the crater. And if you want another sense of scale, see the dude there? Yeah. So it's world famous apart from anyone else in New Zealand who's never done geothermal. So yes, this, ladies and gentlemen, I'll give you the rogue bore. And the reason for that was they didn't have enough casing in the ground. So they hadn't a good enough seal into the dirt. So when the pressure came on, then it escaped out the side. About the same time as that, we had 201, which is about a kilometre up the road, same thing. And that was a mud blowout. They took the rig off, but that still made a big-ass crater. And, over in Carwell, similar era, that's a drilling rig. They copped up there too. This wasn't New Zealand engineers, this is Americans. So they're the only ones to lose a rig. And so what happened was, I think the story was they did their cement job and they all went to the pub. No one was looking after the well. And the well just kicked all the cement out and then made a big crater. The rig fell in. And yeah, Carwell 9, I think, is the only loss of a rig to a blowout in New Zealand history. And we had another one too. This is WK26, which was a well that had been drilled and they knew it had a break in it. It had a break in the casing. And they're cocking around, oh, what are we going to do? And they took forever to go and decide what to do with it. And they put this rig over top of it. And then what happened was the blowout had actually charged up the side of the hill. And the whole side of the hill just blew out. One of the stories was one of the buddy guys says he wasn't running fast enough when it happened because a tree came past him. So yeah, so the whole side of the hill blew out. So that basically, that's the hill debris. And that just blew for years as well. The first directional well they ever drilled in New Zealand was to do a cure for that one. What you do is you come back here and you drill a directional well into where it's feeding from, and you pour cement and you cold water and you kill it like that. So I killed that with a relief well. But yeah, again, Wairiki history that no one knows. And other fun things. Talk about thermal expansion later, and what happened was, we have this used to have a spool on it and it'll allow the inside casing to rise and fall. But they made a mistake and it was just too close to the edge and it wouldn't actually rise up inside the spool, hit the underside of the spool and got hot, and it just tore the threads right off. See those threads? And so what happened was the buddy operators came in one weekend, or after the weekend, sorry, and they found the wellhead like 20 metres away and then that blowing out. So just the thermal effects of casing expansion had blown the whole wellhead off. And yeah, some other fun things. Like I said, black and white photos. So we think we've got it under control now anyway. But so in terms of that blowout 204, valuable lesson is how deep you need to set your casings. So in our fields now, we do a test. So we'll drill a little bit of new formation and we'll find out how much pressure it takes to actually fracture it, to break it down. And we make this a little good graph and nice curve over. So this is a breakdown pressure and we turn it into a gradient. So we call it, this one's an SG. Interesting one is that this one here, 1.0, is all the times we've drilled out and we've got losses. So that's the percentage chances that we've actually had losses in our wells, so we need to manage that. So an important part of my job is just to figure out how far, where do we set these casings, so if we do have the well come under pressure, that it stays in there. And so this is the engineering part behind it, is actually we're collecting data, frac gradient data, so that we know how strong those formations are. That database has got, against depths, fields, formations. And the way I think about it is we've got strong rock, which has a gradient, and normally the deeper you drill, then the stronger the rock. But then you get these zones there that have got permeability, and they're just like free-flowing gravels. So I end up having to build a model to actually calculate how much effective containment for pressure containment you're going to have as you drill deeper. And I've got my little equation now to do that. But that takes in consideration a combination of solid rock and sort of permeable rock. And so feed that into the model, work out how much your pressures are going to have. And so this is the pressure the well can produce. Do my engineering, and this is the pressure that this formation can contain. And so you'll design your well depths based on that. So I need to drill here, it's going to be X pressure, I need to set the casing at that depth. To drill to that depth, then I've got how much pressure that I need to contain, so I need to set the next casing there. So this is how you design wells over depth. So that every step, you start from the bottom and you come back to make sure that you're not going to end up having over drilling your shoe. Because that blowout there, that wasn't like down 1,000 metres, they were drilling at about 300. And they had one casing at 110. I've already talked about, lost circulation. It's a tremendous pain in the arse if you're trying to actually, before you need it. So the issue there is you can't clear cuttings to surface. You're not going to get geology. Drilling engineers don't care about that much. Trouble is that the cuttings, when you're drilling blind, will go out and they'll sit in a formation, they'll sit in a lost zone. But then if all of a sudden you drill into another lost zone, normally that's lesser pressured, and you'll get a big inrush of fluid from the top one and it'll dump all the cuttings down, and all of a sudden you'll just get stuck. So I mean, for us, sort of stuck pipe avoidance is really important. We need to just try and we drill blind, get those cuttings away, and we take that risk. Or you pull out and you cement it up, or you plug it. But the other thing that we can do is aerated drilling. So we're normally pumping with the mud pumps, but if you put compressed air in there, then what happens is it goes in small little bubbles, and when it's coming back up, it expands, and then we can change the density of the fluid column. And so we'll do that so we can actually get fluid pressure to surface. And then what we'll do is, it's basically, you ever got a thing of milk and you've blown air bubbles into it and you've made it all foam up? It's exactly the same. So you can actually lift and overflow the well just by putting in air as well as your fluid. So that's a pressure profile for an aerated column, where normally the water level would only be coming up to 400 metres. We can actually put in compressed air and we can bring it back to the surface. And that gives us cuttings, it cleans the hole. A stuck pipe risk is really minimised. And cementing. So because I said we've got to contain thermal expansion stresses, if we had an uncemented section, then you end up with these buckling situations. Your short section and it goes fat, and you end up with this, getting a helical buckling, and it will actually, because the stress is involved, it will actually completely fail. So to actually prevent that, we need to make sure the casings are cemented top to bottom, 100% held in line. So that's really important for actually, for a well construction. And the number one cause of cock-ups in geothermal well construction is bad cementing. So we put a lot of effort into cement placement. This is from a class that I do on it, but we end up doing it into 3 stages. A primary, so that's just enough to get cement around the bottom. This is in situations where you've got lost circulation. Wherever you pump, it's not coming back up. So what we'll do is we'll go and fill up around the bottom. We do a backfill, which just sort of tops it up into the next casing shoe. At that stage, when that's set, we can just fill it up to surface and maybe a little bit of top hop. But we've got really quite complex procedures to sort of get these things cemented properly to avoid this sort of situation. And it still happens. If you do get a little bit of water trapped in there between 2 casings, it's got nowhere to go, it cannot boil. Because when you get hotter, then the pressure comes up, it won't boil, and it just acts like a big hand. So this is actually an imploded casing. So what actually happens is just one side of the casing will just pop in. And example is, then we have to mill this through. This is exactly the same bulge. Mill it through and you can see there's no cement in there. So, you can render an entire well written off or in need of $2 million worth of surgery by a small sort of error in your cementing. So just making a big effort to not get any water down there and get the cement jobs done properly. And I mean, perfectly honest, contact, we've got a 95% success rate. I think we're still sort of world standard, but it still happens, and that's one of my wells. Temperature, we have to derate all our stresses and our yields and everything for the temperature. cementer. And so if we do get the thing fully cemented in, then the casing still wants to expand, but it can't. And so you end up with this like quite complex sort of shear state inside the cement, preventing it from expanding. Now, it wants to expand, but it can't. So it's like equivalent of allowing it to expand and then getting a big hydraulic jack and pushing it back down to the original place, and you end up with really high stresses. I mean, was I working out 2.5 megapascals per degree C? So if you work out what your standard sort of yields are, the casing goes into yield. Connections have to be strong enough to withstand that. This is sort of a cross-section of a variety. We've got ones with a little gap where the stresses go through the threads, and that's an air gap there. When they first built Waraki, these weren't strong enough and they'd all break. We've got ones now that the threads are strong enough, but we've improved that and we've actually changed it so the load path goes straight through. The couplings don't do anything but keep the two ends together. Sorry, home stretch hopefully. So this is our normal, this is your normal steel kind of chart. This is equivalent to temperature, and this is equivalent to like load. Now we've got a failure point somewhere up here, and so we'll heat it up, and then we'll actually get up into this sort of plastic range, and put it to yield. And then what happens with the casing walls? It's either going to get fatter if it stays in a straight line, but what you can actually see is it gets this sort of kind of buckling, kind of like rings. You can actually look down and see these rings. It's trying to absorb the length, and so you end up with these rings down there. But yeah, the poor old casing, it's under a hell of a stress. It just, the fact of cementing and heating up is really kind of like really makes it hurt. Cement gets radial cracks as well, so eventually you're going to have some degree of flow behind it. I think you can avoid that. I don't care too much about that. And of course, you've got creep. So you get it all hot and it's all under that incredible compressive stresses, but over a period of months, creep takes that stresses back down to zero. And now you're at risk of wrecking your well by quenching it too quickly, to cool it quite quickly. So, we've got to be really careful with our heating and cooling cycles just to do our best just to look after the wells. And do that a few times and you end up with low cycle fatigue. You put it into a compressive yield, and then it gets neutralised, and you cool it, and then you put it into a tensile yield. And you go through that cycle. And it's mostly theoretical, but between 10 and 100 cycles, you can end up breaking your well. So we really like trying to avoid, don't cool the well or don't change the well unless you really have to. I don't think anyone's really seen this sort of failure in New Zealand, but everyone's paranoid about wrecking. What ends up being a bloody big investment for us for that, for mishandling anyway. So gentle management of it is important. And the casing connections I showed before, this is based on what we've seen in downhole videos. They can eat themselves alive, and that's what will happen to your casings. Not necessarily just with thermal, but if you get subsidence, because the ground level's dropping away. So we need to generate power. So we've got unit energy, kilojoules per kilogram, and then what we want to do is to try and get that into the maximum megawatts. We need to get the mass flow rate up. We need a high flow rate. And I did the numbers, and I think a barrel of steam is worth about 28 US cents compared to a barrel of oil is like $100. We need the bigger the diameter to allow the wells to breathe properly is what we're trying to do. So that leaves with bigger final casings. So we end up often in 1338 casing. A lot of oil and gas wells will start in 1338, so we're drilling a lot bigger wells. So you look at the things that play against us. We've got like larger final casings. We need more casings normally. So we're starting at a bigger hole size, means we need a bigger rig. We have lost circulation and drilling problems in those bigger hole sizes. So it gives us drilling problems, and we've got a low ROP. So our wells can be pretty expensive, $7 to $10 million. You've got a whole bunch of temperature issues on your tools. You've got electronics down there. If you let them get too hot, they're just going to burn out. Things like drill bit rubbers and elastomers don't like it, so we've got to spend a lot of time nursing all our tools and keeping everything cool and being really careful about what we run. So we don't have the luxury of running a whole bunch of really fancy stuff that they might have in the oil and gas industry because it's just going to get cooked. And when I say cooked, The electronics in one of those, if we burn that out, that's like sort of $600,000 like bill we get put on by the contractors. So we try and avoid doing that. Temperature profile, everyone thinks, well, you're down at 220 degrees C, so the tool's are going to see 220 degrees C. No. You've got the circulating system, so the temperatures you actually expect to see will be a lot less. So we can use circulating and cooling at surface just to actually manage the tools downhole. So temperature in and temperature out are quite low, but the bottom will circulate and will come up, but it's like this heat exchanger effect. So, but just because it's like 250 degrees down at the bottom doesn't mean that that's what the tool's going to see. But if you shut everything down, it will. It'll heat up like this. Yeah, so if you've cooled the well for a long time and you shut down your pumps, you expect to see this bottom line here. So it's going to come up quite slowly. Now, if you've only drilled and cooled it for a short amount of time, then the conductive heat is going to come up quite a lot faster. But if you've got a zone where you've got two zones coming like this, and all of a sudden you shut down the pumps and the hot water rushes in, rushes down and goes out the bottom, then you've got convective heating, and then you end up with this. And the only time we've ever written off a downhole tools was like that. Within 5 minutes, we shut down the pumps, the temperature rocketed. You could actually see it when we pulled it out, the temperature's just gone off in about 2 or 3 minutes. And all that was just a massive inflow of hot fluid rather than just that conductive. So convective was really what killed it. But, we understand this, you manage it. Formations, sorry, I'm nearly finished, guys. Formations are really abrasive. So this is a tool joint, that's the end parts of drill pipe, and that stuff there is some hard banding, which is supposed to protect it from wearing down. So they went in looking like that, and they come out looking like that. And it's so thin, we're surprised we even got that one out there. So it's really abrasive down there. It's like just high friction factors in it really wrecks your gears. It's like geothermal was just so hard on downhole gear. And hole collapse. So you end up with a situation here, where you've got a weak zone and you're drilling away and all of a sudden all that stuff just falls in around your bit. And you try and pull out, you can't. And you try and pump, and normally it's the loss zone at the bottom, so everything's going out the bottom there as well. So here's a caliper log just showing an example. Nice gauge hole, and then we end up with these giant washes out. And the fact that they're flat just means that the tool arms are just sitting in fresh air. They're not doing anything. So the hole is bigger than that. So yeah, we always run these logs and get a good understanding of what's happening. But it's kind of cool. But yeah, hole collapse has been the bane of my life, I think. 6 months, on one project we lost 6 months and $10 million due to hole collapse. It's insidious. And that leads to stuck pipe, and I particularly love this photo. This is not my rig, all right? But everyone's so desperate to go and get the drill pipe out. These guys are actually having a prayer ceremony to, please God, release my pipe, which I don't actually understand the engineering basis for it, but good luck to them. And I never did find out if they actually got their pipe free or not. But I'd give them, big up, trying everything. It's not in the normal toolbox anyway. But if you get stuck and you're getting really fucked off with your well, see this is here? It's a whole bunch of smashed steel, because the most satisfying thing you can do is throw down a fucking explosive bomb, blow the shit up, and pull out a hole. And it's like, you're like day 3 or day 4, and you're getting really, really annoyed. You're getting really fucked off with this well. It won't come, it won't play ball. So you go down there and you just blow stuff up, and you come free. And then it's pretty satisfying anyway. Not very often, but you can see the size of that. That's like probably an 8-inch on the outside and 3-inch. So that's a whole bunch of steel that we just blew apart. So it was good. And like these things become like ornaments in every drilling office. You've done one and they sit at the front door.
You then have to drill in a different direction to bypass what you've left down the hole.
Yep. So you normally spot a cement plug, hard cement plug, go down, and you might get one of those motors and you'll nudge off it, and you'll sidetrack past it. So, I mean, there's a lot better. Prevention is better than cure, so, we spend a lot of time preventing that happening. But, yeah, you have to carry on and get away with it well sometimes. We're governed in New Zealand by a code of practice. It's the only one in the world, And it's kind of a de facto world standard as well. And that's got a whole bunch of interesting stuff. It really covers sort of like the key parts of any well operator, contractor or regulator might want to see. I was lucky enough to be involved and did a lot of the rewrite on the well design part of it. But yeah, that's really handy around the world. We're trying to tout it. And when you finish drilling, the well is produced and produced. And have you ever been to Rotorua or those places, you know, with that sinter, you know, you get like whole, you know, silica things build up? Well, that happens downhole. So the wells slowly choke themselves up. It's like fatty food and clogged arteries. After a while, they start to deteriorate. So this is like scale. This is silica scale inside a well. And that's preventing the well from producing at sort of optimum rate. So we've got these interventions where you've got to go in and clean it out with chemical, mechanical means. And this one here is one of my recently drilled wells, which has had a casing collapse failure. So we need to go occasionally at broken wells, go in and put a rig over it, mill it out, put new casing sleeves. So, you know, once they exist, then you've still got to look after them. You've got to clean them out and you've got to do some maintenance and repairs on them anyway. Example, I guess we think that's use this thing called a coiled tubing, which is a reel of pipe. It's like 3.5 kilometres of pipe without a break in it, and it's basically wrapped into a circle, and you straighten it out and you shove it down the well and you pump into it, and then so that's just continuous string, and then you can put tools on the end of it, but it's just a fast way of running it out of the hole. So we're using coiled tubing now in New Zealand and over in the Philippines. And just, you know, this is a rig intervention where I just put that in because I like the photo. But yeah, you put rigs on to do intervention and sort of work and repairs and that.
What's that coil tubing made of?
Steel? Yeah. Like a reasonable grade steel, but it's got to be H2S resistant. So yeah, it's about 80,000 PSI yield. In addition to, we keep an eye on the wells with logging, and that gives us temperature pressures, corrosion. You know, sometimes we have to run downhole videos and to actually witness what's going on down there. So yeah, that's part of looking after it. I won't go into that. There's a lot of engineering aspects that we do, but a lot of the stuff has got to be laparoscopic surgery. You've got to just guess. You know, you're looking at some dials and data. You're actually dealing with a problem that's like 2 kilometres away, and so yeah, you've got to be quite inventive and creative and something of a keyhole surgeon to try and actually figure out what's happening sometimes. But the engineering aspects of it are really, really interesting. And time to brag. TH32. It's the world's biggest geothermal well. We drilled it about 18 months ago. And that compares to other big wells. So New Zealand owns the biggest geothermal well in the world. So big that when we drilled it and tested it, it made the national news of people complaining about how loud it was. Which some people thought was bad, and I felt incredibly proud about it anyway. Yep. And yeah, it was supposed to be an injection well. It was one of those things that good decision making. It was supposed to be an injection well, and we were struggling, and someone said, well, this is an inflow and it's really quite hot. Yeah, so we turn it around and we turn it to producing well, and yeah, like I said, it's kind of unmeasurable. It's really good. Just a little plug for what Warriki is. I mean, Warriki Geothermal, I said we're a bit of a institute in and of ourselves, New Zealand pioneering kind of place, where we sort of invested and invented a lot of this stuff. We've been doing it for 75 years, and we kind of specialise in sort of bucket engineering and, you know, real practical solutions sort of stuff. We have been innovators and pioneers for a long time, so I think it's an important part of New Zealand heritage. I'm not saying that's me, but, you know, I'm sort of trying to carry on the legacy of what was ever done there. In terms of the well clean-out technology, I mean, we are definitely the world leaders in that now. You know, we basically chemical clean in this coiled tubing clean-out. We've got other countries coming to us and asking for us to sort of like show them and teach them and run their projects in that respect. And we've got a really high success rate. So the reason I guess I was coming here is we're at the STEM Expo tomorrow, and I guess we're looking for drilling engineers as well as many other engineers. Within Contact, we're looking for engineering and people to come and apply, but personally I'm here because we're looking for mechanical or sort of chem pro engineers that we might make good drilling engineers as well. So, we'll be there tomorrow, come and see us. I mean, the sort of people we're looking for don't have to be grade A students. I mean, I only barely got through, and I'm still doing all right. So, yeah, just don't feel like you've got to have straight A's. The best thing I can say is a bit of a touch of mongrel. Sometimes you've got to stand out in the rain, running a job with some greasy roughnecks and get on with them. Get your hands dirty a little bit, be real creative and imaginative. But yeah, sorry I'm a bit over. That's me anyway, so thanks guys. Any questions, for anyone who's not leaving?
How much analysis do you do of the drilling mud that comes back up to the surface to kind of tell you what the hell's going on?
We have a permanent mud doctor. We've got a mud doctor on site, and he measures it up, and he's measuring it about 3 or 4 times a day. So we'll be tracking the temperature in, temperature out to see if anything's changed. But yeah, he keeps an eye on it and makes sure that it's suitable to be reused. And he'll be diluting it or adding chemicals and that. So yeah, we've got a specialist to manage that.
Can they also tell something about which geological layers you're going through as well?
No, you get it from the cuttings. So so we'll take the cuttings and like I said, they go across the what they call shell shakers, which is big vibrating screens. We'll collect those, and on site we've got geologists that will look at them with like a binocular microscope, and so we get a daily report on what they've seen. Plus we've got information on drilling hardness and stuff like this.
So a bit of a bummer of a question, but how does the safety record for geothermal drilling compare with petroleum drilling? Are they roughly the same, or is one quite different than the other?
One gets a bit more dangerous because everything burns and explodes, and often they're on a platform which is hard to get away on. In terms of the guys on the rig, we had a period there of about 3 deaths in 6 months in the 1990s, and they were all oil and gas operations. But I mean, the machines themselves don't care about pitiful humans, So we've got to be really careful to how we operate them to make sure that people don't, get in harm's way. In Warwick, we've had one fatality. A guy was driving a bulldozer and he fell into a tomo. So the ground opened up and swallowed him, but I think he died with CO2. We're probably a little bit safer because it doesn't explode. Yeah.
Do you use perforation guns downhole, or is that oil and gas?
No, we can, but only if we need to. If we've got run a casing and then we've found out that we need to access, something behind the casing was cemented out, then yeah, we'll run in there. And I mean, I don't know if you've probably heard of them. I mean, they're sort of like 9mm charge and they run in about that deep. So yeah, but frequently we don't. They do it as a matter of connecting to their resource, whereas we don't. We just have to get behind casing and we'll do that. No, cool.
How long will these, sorry, I think we need to go, but this is more about how geothermal energy works. So you're accessing hot water which has fallen as rain somewhere else, yeah? And it's travelled underground through to this area, and it's going over a lot of rock that's presumably got lava fairly, relatively close to it. But so how long, what's the lifetime of the resource? Because
it's a good question actually.
the water must be cooling the rock down.
Well, the water's been there a long time. Yeah. You can extract, and what will happen is the pressure in the reservoir will go down. And it's really dependent on the reservoir. I think as the Warwick went down until all of a sudden there was enough deep pressure there that some warm water came in. It hasn't diluted it, but it's kind of, it's renewable and sustainable. Places like Carwell, and they've run that pretty much similar time, and they haven't seen any loss in any pressure down there. So that thing is, whatever recharges there is more than what they're actually extracting.
So we believe it's sort of, some of these reservoirs are effectively indefinite in lifetime.
You could be, yeah. And part of it is just to make sure that you're not over-extracting. I mean, there's stories about in the States where they, the competitive model, they'd all shove their wells down in the same place and it'd be a race to extract, and they'd over-extract and they'd just rape the resource and it was gone. Warwick, 70 years, we brought the pressure down, but it's still flowing. Carwell, it's remained stable. And you've got to be careful. You can cock it up too by putting your reinjections a place where all of a sudden you're diluting the temperature. So the placement of your reinjection is important to make sure that it keeps the pressure up, but it doesn't short track into your reservoir and actually reduce all your enthalpies.
Oh, that's putting additional water.
Yeah, well, it's the water that's come out. We take the heat out of it and we put it back down. You've got to put it far enough away that it's not going to short track back into where you're producing from.
Have you ever drilled into molten rock?
They did in Iceland.
They did in Iceland.
Yes.
The other day,
Yeah, 2,200 metres, and all of a sudden they lost weight, and then they just pushed in, and then they saw this glass come across the shaker screens, and that's why they figured out they drilled into magma, and I think they've done that in I think Hawaii as well.
How deep is the magma there?
These ones about 5 kilometres over there. That was 2,200.
2 kilometres,
Eh?
And you're at 2 kilometres.
We drilled 2 to 3.
2 to 3.
Yeah, so we're a reasonable way away.
Ways to go.
But yeah, no, it's. I always figured if you do that and the well blows out and turns into a volcano, is that the best drilling engineer in the world or the worst? You know, is the volcano allowed to be named after you or the rig? Yeah. Okay. No, thanks, guys. Take care, man.
Background to my questions that my father spent quite a bit of his career working on hot dry rocks
Oh,
in
yes.
the UK, and he ended up really sceptical about it. I mean, I thought it just kind of fundamentally wasn't going to work.
Yes. That's kind of true. You've got to put so much horsepower into actually pushing the water down. 5,000 psi pumps to actually get it started to circulate. Then I mean, your sacrificial losses are huge. So yeah,
So
yeah.
you need somewhere where the water's naturally hot.
Well,
You're not accessing something that's it's already happened for whatever geological reason.
it's a bit arrogant of me, but I mean that's what we're doing here, because it's the low-hanging fruit. And I think that my biggest concern is I think you could make a go of the EGS, the engineered geothermal systems, where you put down an injector and an extractor and you fracture through. But the cost is so exorbitant for the amount of megawatts you get out. I mean, if you...
But it's going to cool down. It's fundamentally, you're going to start cooling down that rock down there, yeah?
Yeah,
Whereas it seems to me what you're doing is you've got water coming over some long distance and it's collecting heat from a much larger area.
and yeah, I mean, it's the hot,
Volume of rock.
the hot water, and the hot water is actually the resource, not the hot rock. Because I mean, the water's heating the rock just as much as vice versa. And then if you're getting recharge from a deeper resource, then you're keeping it, you're getting it out. I mean, we've looked at doing that. You could just put a conductive heat exchange system in there, but I think it's a bit difficult. You're not going to really extract half as much energy as you could if you took the water out. And maybe someone will make a go of EGS in the future, like that hot dry rock stuff.
Right.
I mean, you saw what they did in Australia. They took $1 billion of investors' money and ended up with 4 wells, and I think they had a 500 kilowatt or half megawatt demonstration plant running for a bit after all that. Yeah, so it's a huge amount of money for, I don't know, maybe they'll make it work. But
Yeah, as I say, my dad ended up really sceptical about it, but he spent about 10 years of his career working on it.
yeah, well, we've got a professor of it at work now, and I need to sit down and have an argument with her. Maybe she can convince me otherwise.
The map that you showed early on of where all the plants were, that's all just north of Topol, yeah?
Yeah, they go from Taupo to Kawerau.
Huka is that where the prawn farm is? Because I've been there as a tourist.
Yes.
And, yeah.
Yeah, that's the Wariki Power Station right
There's
there.
a mountain bike park called Craters of the Moon where I went biking. So that probably was on your photo, was it? Or just off?
Oh, it would have been the one showing all our wells, yeah.
Yeah. Yeah. That's quite an interesting area. I've only been there once, as I say, as a tourist. But, yeah.
Oh no, it's a nice place to work and live,
Yeah.
I see that photo with the rig was just taken the other day, and we've got the power. That's from the power station, so we're right by the power station. That's like 20, 30 metres from my desk, which is great,
That's very very interesting talk.
Oh,
Thanks very
I'm
much.
glad I
Yeah.
could.
Thank you very much.
You're welcome. Thank you.
Is somebody looking after you now, or are you?
No, I'm good. I go to my hotel and do a day's work, I think.
Oh, right, okay. Yeah, thanks again. Yeah,
I'm good, mate. Thanks for coming.
yeah, there you go, yeah.